Today we're talking about rational functions. Rational functions are when we have two polynomial functions divided. And so what happens is usually asymptotes are created. What is an asymptote? Well, an asymptote, if you notice this line right here, this dotted line, the graph, this part of the graph and this part of the graph never touch that line. And this graph goes down, down, down to negative infinity, and this graph, part of the graph, goes all the way up to positive infinity. And so because they never reach the same point, that creates this dotted line. It's an imaginary line. That dotted line's not actually part of the graph, but it just indicates that we take this part of the graph all the way to negative infinity and this part of the graph to positive infinity. So they never meet, so it creates what's called an asymptote. We're going to talk more about asymptotes as the day goes. But first, let's talk about the domain of a rational function. Now, we've talked a little bit about domain before. Remember, when we have, let's say, for instance, we have x plus 1 over x minus 2. That top part is a polynomial and the bottom part is a polynomial. And so this creates a rational function. Now, as far as domain goes, our domain has to exclude anything that would make the bottom 0. So if we look here, we're going to take this bottom and we're going to set it equal to 0 and solve. What is the value that would make the bottom 0? Well, that would be x equals 2. So as far as our domain goes, we can have any positive or negative real number except x cannot equal 2. So that would be the domain of this example. Now, we're also going to use setting the bottom equal to 0 to find our vertical asymptotes. Vertical asymptotes are found by setting the denominator of a reduced rational function to 0 and solving for the variable. So a vertical asymptote would be a dotted line that goes up and down, just like I showed you on our bell work. Okay, and so we're going to talk about vertical asymptotes. We're also going to talk about horizontal asymptotes. That would be when we have a horizontal line. That imaginary line, the graph, will approach but never actually meet. So we use a couple of things to find horizontal and vertical asymptotes. We also have to talk about holes. Holes in the graph are found by canceling any of the factors of a rational expression. So what you would do is, like on my example, I don't have anything on the top that would cancel with the bottom, but let's come up with another example. If I gave you this rational function, we could factor the top. We could factor it to x plus 1 times x minus 1 over x plus 1. Notice the x plus 1's will cancel and leave us with just x minus 1. Now, if that happens, the things that canceled, so you notice the x plus 1's that canceled, if I were to take and set that equal to 0 and solve, I would get negative 1. Now, negative 1 is not going to be an asymptote, it's going to be a hole. So it's a hole in our graph. And so it's a little bit different than an asymptote. Moving on to horizontal asymptotes, there's a couple of rules that you have to follow in finding horizontal asymptotes. Okay, if the degree of the numerator is larger than the degree on the denominator, then there is no horizontal asymptote. So I put a little greater than sign to help me remember if my degree on top is bigger than my degree on bottom, then there's no horizontal asymptote. Now, if the degree on top is smaller than the degree on bottom, so less than, then I have an asymptote, a horizontal asymptote at y equals 0. If the degree on the top is equal to the degree on the bottom, then you use the leading coefficients of the top and the bottom to figure out where your horizontal asymptote is at. And we'll do an example. An oblique asymptote. Now these, let me put my equal sign. The oblique asymptote. Now these are found only when case number 1 is true. So the degree on the numerator is the degree of the numerator is larger than the degree of the denominator. So if that's the case and we have no horizontal asymptote, then you always have to check and make sure you don't have an oblique asymptote. Okay, and that would be a slanted asymptote. Let me show you an example. That would be like an asymptote that would go like this, and our graph would, do something crazy like that. Okay, so that is an oblique asymptote, and it's only true for case number 1 on horizontal asymptotes. So you would use long division, and you would divide the two polynomials, and you would get whatever your equation is that you get. That would be without the remainder. That would be your equation for your slant asymptote. Okay, on to our first example. It says, part A says, find the domain and the range of the function. So if I'm looking here, my domain is going to be, remember, I have to toss out of my domain anything that would make my bottom 0. So notice x minus 1 equals 0. The value of 1 is what makes my bottom 0, so I have to throw him out of my domain. So my domain is going to be all real numbers except x cannot equal 1. Okay, so that would be my domain. On part B, it says to complete the table. So what I'm going to do is I'm going to fill in the table with the values. How do I get the values? Well, you just take like 0.5, 0.9, 0.99, 0.999, and you plug it in. So f of 0.5 equals 5 times 0.5 over 0.5 minus 1. When you plug that into your calculator, you get the value of -5. So if I were to do 0.9 and plug in 0.9, five times 0.9 over 0.9 minus 1. That's a point, not a negative. You would get the value -45. So you just fill in your table, and as you do the other two values, you get -495 and -4995. Now notice, as we get closer to the number 1, what's happening here? Well, they're getting closer and closer to -infinity. Okay, now we're going to go on the other side of 1 and we're going to plug in values. So if you take 1.5 and you plug it in, you get the value of 15. If you take 1.1 and plug it in, you get 55. If you take 1.01, you get 505. If you take 1.001 and plug it in, you get 5005. What's happening here? The values are getting closer and closer to positive infinity. So what can we assume about the number 1? If on the left side of our graph we're approaching negative infinity, And on the right side of the graph, we're approaching positive infinity. We can assume that 1 is going to be an asymptote. And so that's going to be part C, is discuss the behavior of f near any excluded values. Well, we know, because if we were to take the bottom and set it equal to 0, we know we have an asymptote at 1, x equals 1. And we can verify that using these tables, because we can prove that the left side goes to negative infinity and the right side goes to positive infinity. So the closer we get to 1, they're doing different things. Negative infinity is never going to meet positive infinity. So we can assume that there is an asymptote. On example 2, it says find any asymptotes of the graph of the rational function. So remember, we have 3 different types of asymptotes to consider. We have a horizontal asymptote, we have a vertical asymptote, and sometimes if we don't have a horizontal asymptote, we may have an oblique asymptote. So we're going to put all 3 of them on there, and we're going to check for all 3. Now remember, the horizontal asymptote rules are if the degree on the top is less than the degree on the bottom, which in this case it is, because we have a degree of 0 on top and a degree of 3 on bottom, then we have an asymptote at y equals 0. Now, let me point out, asymptotes are always written as an equation. So it needs an equal sign and it needs either an x or a y on it. Okay, now vertical asymptotes, we have to find them by taking the bottom and setting it equal to 0 and solving. So if I solve that equation, I know I have a vertical asymptote at x equals 2. Now, an oblique asymptote only occurs if I have no horizontal asymptote. And since I do have a horizontal asymptote, I'm not going to worry about an oblique one. I have none. Okay, so on part B, we're going to do the same thing. All it's asking us to do is to find the asymptotes. So write down your 3 possibilities: a horizontal asymptote, a vertical asymptote, and an oblique asymptote. Okay, so for my horizontal asymptote, notice my degree on top, my highest degree, x squared, is equal to the degree on the bottom, x squared. So what I have is I have 2x squared over x squared if I just look at my leading coefficients, which makes 2, because I can cancel those x squares out. So I know that I have a horizontal asymptote at y equals 2. Now, my vertical asymptote, I'm going to come over here and I'm going to write my bottom, x squared plus x minus 6. Set it equal to 0. I can actually factor that, and there's going to be 2 places where I have vertical asymptotes. This factors to x plus 3 and x minus 2. So if I take both of those equations and set them equal to 0, my left one is going to equal negative 3, and my right one is going to equal positive 2. So I have 2 vertical asymptotes at negative 3 and at positive 2. Now, because I have a horizontal asymptote, I will not have an oblique asymptote. And that takes care of part B. Now, this one adds something. Notice it says, and we're adding in holes, okay? So what I'm going to do is I'm going to set up holes, and then I'm also still trying to find horizontal asymptotes, vertical asymptotes, and an oblique asymptote if it's there, okay? So what I'm going to do is I'm going to factor the top completely, this is what the top would factor to, and then factor the bottom completely, and this is what the bottom would factor to. Notice what on the top will cancel with what on the bottom. My x plus 5s will cancel. So what would have been an asymptote at x equals -5 is now a whole. So I actually have a whole at the value x equals -5, not an asymptote. Now, we'll still continue on and find our horizontal asymptote. So our horizontal asymptote is take the leading coefficients, so x squared over x squared, and that would leave me with 1 over 1, which is 1. So I know that I have a horizontal asymptote at the value y equals 1. Now my vertical asymptote, notice on the bottom, I had the x and x plus 5, but x plus 5 canceled out. So he's not an asymptote, but I still have the x. So x equals 0, that is going to be my vertical asymptote. And I still have no oblique asymptote because I had a horizontal asymptote. Okay, so moving along, it says find the domain of the function, decide whether the function is continuous, and identify any horizontal and vertical asymptotes. Okay, so for part A, all we have to do is we have to exclude whatever would make our bottom 0. So if you notice, our bottom will factor to x plus 3 and x minus 3. So the two values that would make my bottom be 0 are x equals -3 and x equals 3. So what I'm going to do is say my domain is all real numbers except x cannot equal 3 or -3. Now, as far as part B goes, if it's continuous or not. Now, if I have any kind of an asymptote, it's not going to be continuous. If I have a hole in my graph, it is not continuous. So it will only be continuous if neither of those things are present. So in this case, I know my graph because I'm going to have two asymptotes on the bottom and I'm going to have a horizontal asymptote. So I know this is discontinuous. Okay, and then on part C, identify any of the horizontal and vertical asymptotes. Well, I've already identified what my vertical asymptotes are. I have two of them. So I'm going to write vertical asymptote, x equals 3, x equals -3. And then for my horizontal asymptote, I have, if you look at the leading coefficients, that would be x squared over x squared, which is 1 over 1. So I have a horizontal asymptote at y equals 1. And the next lesson on 2.7 is where we're going to start graphing all of these. So it's really important for us to be able to identify them first, and then we will graph them. So if we're looking at part B, this graph, now if you'll notice, the bottom will not factor. There are no factors of 9 that will break down to add to 1. So our bottom will not factor and our top will not factor. So if they won't factor and they won't cancel out, I do not have any places on the bottom that I have to exclude. So my domain is going to be all real numbers. Now, if you were to get your graphing calculator out and plug this in and graph it, which I would recommend you pause right now and do that, you'll notice there's no holes and there is an asymptote, but it doesn't really affect as far as there's not a piece of the graph on the other side of it. So we actually have a continuous graph here. And if that's confusing to you, make sure you graph it out. Now, part C is identifying our asymptotes. So our bottom is never, there's not a place where it's going to be 0. So we have no vertical asymptotes, but we do have a horizontal asymptote. Notice our leading coefficients, the degrees are equal. So we will have a vertical asymptote, and that value is going to be at 3. So y equals 3. Almost done. So we've got one more problem, and this is the application. I copied this right out of the book. It is problem number 47. So if you would like to go and look at the book, if this is hard to read, you can do that. And this is basically a model of a physics experiment where they attach a mass and consider oscillation times. And they have theirs recorded where they have the mass they hung and the time. Now, they also give us a model. So what they're on part A, what they're wanting us to do is to verify that the values that they took, the times that they received, do come close to the model that they created. Now, it's not going to be the exact same time. It's going to vary just a little bit, like they're off a little bit. So what you're going to do on part A is you're going to create a table with your mass and with your time, and use the same masses that they use. So do 200, 400, 600, and so forth. So you complete that yourself. And then you're going to actually take the time, you're going to take those values and plug them in and into the model that they give you, so that equation down there, and you're going to actually get the value. It's going to be off just a slight bit from the one that they give you, but it'll be close enough to where you can verify, yes, that would be a good model to use. On part B, what it asks us to do is it asks us to find the mass of an object when the average time for an oscillation is 1.056 seconds. So what I'm going to do is I'm going to use algebra, and I'm going to set my equation equal to 1.056, and I'm going to solve for m. And there we have it. So we're going to walk out the steps for that. So I'm going to put this under 1 and cross multiply. So this would give me 10 times 1.056 gives me 10.56 m plus 52,800 equals 38m plus 16, whoops, I'm running out of room, 965. So then I'm going to solve by moving my m's to one side and getting my numbers to the other. And when I do that, I get this, 27.44 m equals 35,835. So m equals 13.0, it's 5.9, so I'm going to round to 06. So that would be the mass that would give me the oscillation time of 1.056. Now if you look on your chart, 1306 falls right, there, and so that does make sense because that's about in the range that we would need. And there you have it. That takes care of rational functions for today.